So this is problem 342. So if we look at the problem, it says the position of a dragonfly that is flying parallel to the ground is given as a function of time by the vector r, this position vector, this function of time, is equal to 2.90 meters plus 0.0900 meters per second squared times t squared I minus 0.0150 meters per second squared t squared j. So it's parallel to the ground, which means the z coordinate is constant, so that's why we don't include z, but it can move in the x and y direction. So if you think about it, we have a three-dimensional situation here. We have x, y, and z, and it's somewhere z, and it's traveling at a constant z level, but the x and y can change, which it does. At what value of t does the velocity vector of the dragonfly make an angle of 30 degrees clockwise from the x-axis? So let's think about that. Let's just draw the coordinate system in the xy direction. So 45 degrees, pause 30 degrees clockwise. So clockwise is this way. 30 degrees. And the direction, the velocity vector, is going to be the derivative of the position vector. And what we need is for the position or the velocity vector to be in the same direction as this vector here. So we need to come up with this vector, which we'll just call it we'll call it p vector. And the p vector is not a function of t, it's constant. And if you think about this is the opposite side. So this is going to be the sine of 30 degrees because it's opposite times, well, we don't have to multiply it by any kind of length. We just have to have the direction, and this is going to be the cosine of 30 degrees. But it's going to be, this part's positive, but this part's negative. So we'd have the sine of 30 degrees, cosine of 30 degrees. This is the cosine of 30 degrees I plus minus, because it's going down, minus the sine of 30 degrees j. And we need this thing to be going in the same direction as this position vector, which is 30 degrees from the positive x-axis in the clockwise direction. So let's calculate the velocity vector as a function of time. So if you take the derivative of a constant, you get 0, and the derivative of this is going to be 2 times 0.0900 meters per second squared t I. So what you do is you take the derivative of t, which is 2t, so you get 2t, times this constant, and it's still in the I direction. And then you have negative, so you'll have negative 2 times 0.0150 meters per second squared times tj. Okay, so let's multiply it out. So we get our velocity vector as a function of time is going to be equal to 0.1800 meters meters per second squared t times I minus 0.0300 meters per second squared times t j. So, and all we have to do is we just have to have these in the same direction. But because t is the same in both of these, then it would seem that that ratio is going to be the same no matter what t is. Except for t equals 0, they'll both be 0. So I'm not sure how that ratio changes. So I'm going to just pause it, think a little bit here. Okay, you may have already figured it out. And I should have realized it from the units. I got two things wrong. So, I didn't correct this because it's, again, I'm trying to demonstrate where you can find error, where you can kind of catch errors. So I forgot it was t cubed. So that means they do change. The ratio of these things do change. So now when I take the derivative of this, I'm going to get 3 times that constant times t squared. And if I get to this point, and this is, so 3 times that is going to be 0.0450. So 3 times 0.015 is 0.0450, and this is t squared. So the question is, what value of t is the ratio of these two the same ratio as these two? So let's put those in there. So here's your position vector. The cosine of 30 degrees is going to be 0.866, which is equal to the square root of 3 over 2. And the sine of 30 degrees is 0.5. And so what we have is, if we take the ratio of these two things, so we'll take the ratio of these two velocities. So you get 0.1800. I'm going to leave the units off here. T divided by negative 0.0450 t squared. That's got to be the same ratio as the ratio of these two components, like that. And this one is negative. Okay. So now you can see I can cancel that t with that one of those t's. Let's cross multiply and then solve it, and then we'll double check our answer. Make sure we did all this correct. So if you take 0.18 times 0.5, so this cross multiplication here is you get negative 0.09. If you cross multiply this way, you get 0.0450 times 0.866, which is negative 0.03897. I'm going to take an extra significant figure, and you've got a t left, so now we divide both sides by negative 0.03897. You see the negatives cancel out, which is good because I need a positive t. And so I get t is equal to 2.31 seconds. Okay, so let's try that out. So if I plug, let's do it up here. So if I do t of 2.31 seconds, that's going to be equal to 0.18 0.00 meters per second squared times 2.31 seconds, I, minus 0.0450 meters per second squared times 2.31 seconds, J. So we get 0.18 times 2.31, so that's 0.416. And this seconds cancels out one of those, so you end up with meters per second. I, and then the next one is 0.0450 times 2.31, which is 0.104 meters per second, J. And that does not seem to be right, because I'm thinking if you look at the ratio of these two numbers, that's not the same. So, oh, it's because this is t squared here. I keep forgetting that squared part. And this is cubed. Okay, so again, I'm leaving that in there. I looked at the ballpark. So you get 0.0450 times 2.31 squared, and I get 0.240 meters per second, J. Okay, so let's draw that vector, just sketch it. So it's going to have a positive x component and a negative y component, like that. So the x component is 0.416 meters per second, and the y component is negative 0.240 meters per second. And this angle is theta, which should be 30 degrees. And if I take the inverse tangent of negative 0.240, that's opposite over adjacent. Make sure my calculator is in degrees. So let's take the inverse tangent of negative 0.240 divided by 0.416, and I get negative 29.98 degrees, which is 30 degrees, negative 30 degrees. So that does work out. So let's kind of review what we did now that I know I did it right. So what we said was that the velocity vector is the direction that the object is moving. I'm not sure what I just said. The velocity vector, which is the derivative of the position vector, is the direction that something moving, and we want to find the time when it's moving at 30 degrees relative to the positive x-axis and in a clockwise, which is this way, clockwise direction. This would be counterclockwise, so it's pointing down. So I used this position vector. This is a unit position vector to represent negative 30 degrees. So I had the cosine, which is the x component, which is the adjacent side, times I, minus the sine of 30, which is the opposite side. So that gives me the direction of that I'm trying to have this happen. So I take the derivative of the position vector. This goes to 0. Here we get 2 times this times t, I, and 3 times this times t squared j. So that's this calculation right there. And let me just go through and fix all the things I don't quite have right. So this was cubed. Okay. So if I multiply it out, I'll get that. And you see if I stick t in here, t's in seconds, so that simplifies down to meters per second. Here I put second squared in, so that simplifies down to meters per second. So that's the function. And what I said was the ratio of these two here has to be the same as the ratio of those two to give me the same angle. It's kind of like similar triangles. You know, if the ratio of this to that is the same as the ratio of this to that, then we have a similar triangle. And because one involves t squared and the other involves t, that ratio changes with time. So I solved this equation for t, which gave me 2.31 seconds. So then I evaluated the velocity at 2.31 seconds to get that, which then I made up a velocity triangle with the values, the x component and the y component. And then because the angle I'm measuring here, these two sides, the opposite over the adjacent is the tangent, I'm going to take the inverse tangent. And because I have a negative sign here, I'm going to get a negative angle. And it all works out. So how about that?